Okay, so we are going to find the electric field everywhere due to this point charge Q at the origin. We're going to build a Gaussian surface that exploits the symmetry. We want the same kind of symmetry that our charge distribution has. In this case, it has spherical symmetry. So my Gaussian surface is going to be a sphere of radius r, centered at the origin. That was a terrible looking sphere. I'm going to draw that again. That's not much better, but it's a little better. So sphere, radius r. Okay. Now, I got to make a couple of arguments here. First, I have to note that the electric field will point away from the charge. I would say it points radially outward from the charge. So the electric field is going to be pointing out like this. Everywhere along the sphere, the electric field is pointing tangential to the sphere. Okay, then I got to note the magnitude of E must be constant on the surface of the sphere. Let me put in there, on the surface. How do we know that? Just a logical argument. This nature doesn't know which way I put my z-axis. It wouldn't make any physical sense for the electric field to be bigger up on the top of the sphere than the bottom, because there's nothing special about the top. We said we have spherical symmetry, so the electric field, whatever it is, must be the same everywhere on the surface. Now, it doesn't have to be the same everywhere in space. It might be bigger when I get closer to the charge and smaller when I get further away. The universe knows the difference between close and far. The universe doesn't know the difference between this spot and this spot and this spot, all these spots on the surface of the sphere. Okay, next we find our normal vector. Our vector perpendicular to the surface. I'm going to draw that in a different color. Maybe blue. So let's draw in some of our normal vectors perpendicular to the surface. They're going to point out like this. Hey, that's the same direction I drew E in. So next we note my E vectors are all parallel with my normal vectors. That's an N hat I'm drawing there. Those are all important. Then, Gauss's law tells us that the triple integral of my, here, I don't want, I was going to rederive Gauss's law. I don't need that. The E dot ds, the double integral of E dot ds, must be equal to the charge enclosed divided by epsilon naught. This is my flux through the surface on the left-hand side. Because these E is parallel within my surface vector, because these two vectors, that and that, point in the same direction, because those two are parallel, the dot product is just the magnitude of the, or the product of the magnitudes. I was able to make this step because of this line right here. So maybe we'll number these. I, and double I. So because of double I. If I'd picked a different Gaussian surface, that wouldn't be true. If I'd picked a cylindrical surface, E and N would not be perpendicular everywhere, and I wouldn't be able to do anything. Wouldn't even be able to make this first step. Next, magnitude of E is constant. It's just a number on the surface. I know that because of I up here. Double integral of ds, that's just surface area. That's what that means. That means find the total surface area of my Gaussian surface. That's 4 pi r squared. Okay, what about the right-hand side? Charge enclosed. How much charge lives inside my surface? And it's all right there. I called it Q. That's just Q. That's all the charge I have. It all lives inside the surface. So now I can put those two together. E times 4 pi r squared equals Q over epsilon naught. Don't forget your epsilon naught. And so magnitude of E equals Q over 4 pi r squared epsilon naught. That's the magnitude. I already know the direction. I know it points radially outward. I figured that out just by looking at my symmetry. Wait a minute, that kind of looks familiar. You may recall K is just 1 over 4 pi epsilon naught. So that formula really says KQ over R squared. That's Coulomb's law. I can never spell Coulomb. You'd think I would know how to spell Coulomb. I can never remember if it's O-U. Yeah. I want to write C-O-L-O-U. I want to put the U with the second O every time. We have just derived, we've proven Coulomb's law. This is where it comes from. Okay, 2, let's do a sphere of charge. Total charge Q and radius capital R. So I've already done this problem. I'm doing all the different Gauss's law problems all together in one video. I think you've already watched this video, in fact, but we're going to do it again. So I've got some smeared out charge here. Radius capital R. I want to find the electric field inside, literally inside the charge itself and outside. So way out here. So first, let's do inside. I'm going to draw a Gaussian surface that has the same symmetry as my charge distribution. I've got a sphere of charge. Our Gaussian surface should probably be a sphere. So I'm going to draw this nice and big here. Here's my charge. That's radius R, capital R. I'm going to draw a Gaussian surface that lives inside there. So it's going to be a sphere of radius R that lives inside here. So little r, which is my variable. Big R is, it's a constant. It's not going to change. My variable here, my one and only variable in the problem is little r. And it's smaller than big R. Okay, so let's draw that. There's my little sphere. He has radius, little r. I only care about what's happening on the surface of that little sphere. So first, we got to make a couple of arguments. E must point radially outward. Again, that's by symmetry of the charge distribution. It's a sphere, so the electric field has to have spherical symmetry. E must point everywhere out, even inside here. Now, maybe we're going to end up finding out that E actually is constant everywhere inside, but the direction, we're not, but the direction has to point away from the origin. It's the only kind of picture I could draw that has the same symmetry as the charge. So like even out here, all my E's are going to be pointing away from the origin. Even on the surface, which is where I actually care, E will point away from that surface. So we draw a few of those just to illustrate that. Secondly, in magnitude, in strength, E must be constant on the surface, the blue surface I drew here. This one's a little harder to think about. But again, it's just using logic. We're not proving this using physics. We're proving this using logic. The universe would be really weird if the electric field were bigger up here on the z-axis than it is down here on the negative z-axis. So I've got some perfectly spherically symmetric charge distribution, but for some reason, the electric field gets bigger as you go up the z-axis. The universe doesn't care where I put the z-axis. I could flip my z-axis over. The universe wouldn't know that. So what would be special about the z-axis? There's nothing special about it. The electric field has to be the same strength everywhere here because the universe treats all those points the same. This point way out here toward the edge of the charge is different than this point down toward the center. Those would be different. The universe can tell the difference, but it can't tell the difference of points here on that surface. Okay, what about the normal vectors to my surface? Maybe we'll draw those in purple. So here's a normal vector. Remember, normal vectors on closed surfaces always point out toward the infinite part. You'll never have normal vectors pointing in. They always point out toward the infinite volume, not the finite volume. Hey, that's the same direction E pointed, radially out. So on the surface, E, the vector, points in the same direction as my normal vector. Or another way of saying that is E is perpendicular to the surface. Those mean the same thing. Okay. Then the left-hand side is a lot like the last problem. We're going to have, I'm trying to switch away from purple. We're going to have the flux through the surface is the double integral of E dot ds. Because of number one, those are, no, sorry, backwards. Because of number 2, the dot product of parallel vectors is the product of the magnitudes. So I lose both vectors. I lose my little dot product symbol there. Because of this one, I can pull that E out. Double integral of ds is just surface area. We're talking about a sphere here. So the surface area of a sphere is 4 pi little r squared, the Gaussian surface, not the big chunk of charge. I'm doing a surface integral over this blue. And his surface area is 4 pi little r squared. What about the right-hand side, Q enclosed? Here's where the work happens. Q enclosed is always some charge density times some kind of volume enclosed. We're going to have 3 different versions of what we mean by volume enclosed. So we're going to think generalized volume here. If our charge is just a line, then my volume enclosed will be a length. If the distribution is a surface, it'll be an area. If the distribution is some volume, it'll be a volume. So I'm only trying to figure out really what we're doing mathematically is I've got a total charge of capital Q spread out here. I want to know what fraction lives in the blue sphere. If this radius, by the way, if this were half of the whole thing, if I came out halfway, I would have 1/4 of the volume in there. I would have 1/4 of Q. But that's not what we have. Okay, so let me draw a couple of pictures here and motivate this. Here's the total R. And then I've got my little one inside. Little r. That little r is not showing up. My charge density the way I like to think about this is these two need to multiply to give just units of charge, just coulombs. So I'm going to be multiplying this guy by volume. This has to be coulombs per cubic meter. So that when I multiply by volume, coulombs per cubic meter times cubic meters gives coulombs. So this is charge per unit volume for the entire sphere. And that's going to be the total charge divided by the total volume. The total volume of the entire thing. That's how dense the charge is packed into this sphere. What's my volume enclosed? How much charge do I actually care about? Just this stuff. That's all I care about. That volume is 4/3 pi little r cubed. So then my charge enclosed, the fraction that I've captured just here in the blue is density times volume enclosed. The 4/3 and the pi cancel out. I get Q, r little r cubed over big R cubed. That tells me what fraction of the total charge lives inside the blue sphere. If these are equal, by the way, if the blue sphere is all the way out here, if little r equals big R, look, those will cancel and I'll just get 1 times Q. I get all my charge. Okay, so now I can put these two sides together. So the double integral of E dot ds, which we worked out up top, was this, must equal charge enclosed over epsilon naught, which we just worked out is this. So we get magnitude of E equals Q little r cubed over 4 pi r squared. Again, an epsilon naught, an r cubed, and some of those r's cancel out. We get this. That's the charge. That's the electric field, the strength of the electric field, a distance little r from the center. And that ranges, that's for r between 0 all the way out to the boundary. In fact, we could even check what happens at the boundary. We could plug in little r and we get Coulomb's law, essentially. Okay, now what about outside? That's we're only halfway done with that problem. Outside. So now I have to draw a brand new picture. So everything I'm writing is required for a complete solution on these. Here's my charge distribution, capital R. Draw that to make that look like a sphere. Now my Gaussian surface is going to be outside. It's going to be out here. Here's little r. So now little r is bigger than big R, which is a weird sentence to say. Okay, so most of the math is the same. For all the same reasons. I don't even need to justify all the reasons again. Double integral E dot ds is magnitude E, double integral of ds. Remember, we're integrating over the blue here. So that's E 4 pi little r squared. That's the surface surface area of the blue sphere. What about charge enclosed? What fraction of my charge lives inside the blue sphere? All of it does. The charge only lives right there. All the charge lives in there. I know how much is in there. It's Q. So we put these two sides together. Q over epsilon naught. And we get magnitude of E equals Q over 4 pi r squared epsilon naught. That's for r greater than r. Okay, so that's the sphere. We should point out here. The vector E in both cases points radially out. Okay, let's do a line of charge. With charge density, lambda. So we have an infinite line of charge here. I can't tell you the total charge. I can't say total charge Q because it's infinite. We have an infinite amount of charge with this density, and that density is it's a linear density in coulombs per meter. So I've got some infinite charge here. Charge density lambda. That's an ugly lambda. Make that guy a little prettier. Okay, we've already done this problem using Coulomb's law. It was a pain. It was hard doing the integral to find the electric field from a line of charge. It's really difficult. I'm going to do it now using Gauss's law instead, and it's so easy. So we draw a Gaussian surface that has the same symmetry as a line. Remember, I need some 3D surface here, 3D object, and we're looking at the surface of it. The only object that has this kind of symmetry is a cylinder. Cylinders have 2 dimensions. So let's say length L, radius R. Let's draw this guy in blue. That's what I've been doing. So here's radius R. Oh, that was an ugly straight line. Here's length L. Notice that I am drawing pictures and I'm labeling them. All of this is required on the work you turn in. You're going to be doing the cylinder of charge. You got to draw labeled pictures, and you got to make the following arguments. Everything I'm writing out, I'm showing you complete solutions here. Okay, so first, E must point away from the line. In a perpendicular fashion. It wouldn't make any sense. Imagine if we got an infinite wire and the electric field points up at some angle like this. Like what? The universe wouldn't care about up versus down. I could flip my wire around and now the electric field will point down instead of up, but the scenarios look identical to the universe. That wouldn't make any sense. What angle would it point up at? Like none of that would make any sense. The only thing that logically that has the same symmetry is if the electric field points away from the line. So E must point out like this. So let's draw some of those over here. Even right here, like at this spot right here on this cylinder, it's coming straight out at your eyeballs. On this spot in the back, it's pointing straight away from your eyeballs. I can't draw those. Also, in magnitude, E must be constant on not these end caps, but on this outer sheet. I should say on. See, a cylinder has 3 different surfaces. We've got surface 1, which is the top. We've got surface 2, which is the bottom. Think of a soup can, the top and bottom of the soup can. And then you've got surface 3, which is the label of the soup can. So when I say outer surface, I mean the label. Why does E have to be constant there? Where did this come from? All those points on the label, all these points out here are all the same distance from the line. There's no reason why a spot up here would have a bigger electric field than a spot down here. They're identical as far as the universe is concerned. It's an infinite line. It doesn't care about this spot versus that spot. These spots are different. A spot in close versus a spot far away. Yeah, the universe can tell the difference between close and far, but not spots here along on the label of the soup can. That's not true up here. E does not have to be constant. In fact, E is not constant up on the top or the bottom. Okay, what about my differential elements, my normal vectors? Let's do purple. My normal vectors point perpendicular to the surface. So I'll have one right there. I'll have another one pointing out here. Down here, my normal vector points perpendicularly away. Up here on top, the normal vector will point up. So I'm drawing some of these. Okay, so notice up here on surface 1, let's redraw that. So for surface 1, I've got the top of a soup can here. E is pointing like this. My normal vectors are pointing like this. Those are perpendicular. The dot product of perpendicular vectors is 0. Up on that surface, E dot N is 0. The dot product of perpendicular vectors is 0. So the flux, let's call it flux number 1 of E dot ds, that's just 0. The flux up on top is 0. Similarly, for the same reason, look down here, E's parallel to the surface, perpendicular to the normal vector. Flux number 2 must be 0. No flux flows through the top or bottom. All the flux flows through the label of the soup can. So in section 3, E is parallel with N, perpendicular to the surface. So the flux, let me write flux here, E dot ds will be first, those are parallel. So we get product of the magnitudes. We drop the little vector arrows. We drop the dot product. We just got an absolute value there, or magnitude. And I already said that E is constant on that soup can label. Because it's a constant, I can pull it out of the integral. So now I just got to find the surface area, not of the entire cylinder, only the surface area of the part that's contributing to the flux. That's the label of the soup can. So let's think about unwrapping this label. Imagine, like, literally you're pulling the label off a soup can. You slice it here and you unwrap it. It'll be a rectangle. It'll be L high. And the length of that rectangle will be the circumference of this circle. So that surface area there, the surface, if I unwrap it, I just can't draw a straight line to it. It's L high and 2 pi r long. So area there, this is just area. Excuse me. RL. Okay, what about the right side of our Gauss's law? Our charge enclosed. Q enclosed is always some kind of density times some kind of, I'm going to put this in quotes, volume, some appropriate version of volume enclosed. Our density is in coulombs per meter, so my volume element here will be meters. It'll be length. All of my charge that I'm looking at here lives along this line. It's right there. There's the charge. How much charge did I capture? How many coulombs of charge? The density, lambda, times that length. So this will be lambda. That was my charge density times the length. So putting these together, flux equals double integral of E dot ds equals charge enclosed over epsilon naught. We get magnitude of E times 2 pi RL equals lambda L over epsilon naught. Notice the L cancels out. It has to. The L I made up was arbitrary just to draw this Gaussian surface. The L can't possibly appear in my answer. The charge, the electric field at some point in space here should not depend on how big I decided to draw my cylinder up and down. It may depend on how far away I am. So I kind of expect to get an R in my answer, because the further away I am from the charge, I would expect the field to go down. But the answer can't have anything to do with L, because that was just an arbitrary dimension for my surface. Well, look what happens. The L cancels out. And I get the electric field from a line of charge is lambda over 2 pi epsilon naught. And it points away from the line. All right, let's do a sheet of charge. I think we have a written assignment on this one later. I think like you guys actually have to write this one up. I'm going to do the whole thing for you right now. I just want you to write up all the details. So let's say we have a sheet of charge density. Sigma, this is going to be an area charge density. Let me draw a better sigma there. In coulombs per square meter. So I've got some infinite sheet. This goes on forever. Of charge density sigma. I want to find the electric field some distance away from the sheet. So I'm going to draw a Gaussian surface. I actually have a couple of options here. I want to exploit the symmetry. I could draw what's called a Gaussian pillbox. Okay, so I'm going to try. I always have trouble drawing this one. So I'm going to do it two different ways. So let's say first way, a pillbox. So here's my sheet. I'm just kind of showing a little section of the sheet. I'm going to draw, let me do this in blue like I have been. Here's where I'm intersecting. I am not a good artist. And then it comes back here. Okay, so what I've drawn is I'm going to draw that a side view, some box that looks like this and sticks out. So this is a side view. So we're looking down the plane here. The plane is coming right through our foreheads. Okay, I need to give dimensions on everything here. So let's say I've come out some distance, maybe h. That's how far I came out. This total height here, so this would be h here out and another h back. So h in front, h in back. This guy here, maybe we'll call L. That would correspond to this. And then width here, which we can't see in this picture, it's kind of going back like this. Here would be width. All of my charge lives in the little box right here in the intersection. So let me try to draw in the charge itself, maybe in green. Here's the actual charge that intersects my pillbox. A little rectangle right there. Half of my pillbox extends in front of the plane, half goes behind. Okay, some arguments. First, E as a vector must point away from the plane. It has to. It wouldn't make any sense otherwise. Imagine if the electric field points up at some weird angle like this. And this is an entire plane. Why would the universe want the electric field pointing up at some angle if I rotate that plane around? Like imagine a sheet of paper right in your, down your nose, in your forehead, and you rotate that plane forward. That wouldn't make any sense for this electric field to now rotate around, because the universe would say, well, that sheet looks exactly like the other sheet. Now E must point away. It's the only thing that has the same symmetry on both sides. E must look like this. So over here, E is pointing away. And back here behind, E is pointing away. If we come further away, maybe it drops off. Maybe it gets smaller as we get further away. We don't know that yet. The universe will know the difference between distance here and here, but not locations. E must also be constant. On these front and back faces. So now we've got 6 different faces here. I'm going to have to find 6 different fluxes here. But E must be constant on faces 1 and 2, the front and back. That would correspond to here and here in this picture. Well, what about the other ones? Well, we won't care about the other ones. Let's draw some of our normal vectors. My normal vectors are going to point out away from the surface. I say up here on top, for example, see my normal vector points like straight up. Over here, the normal vector points out like that. So on this front surface on 1 and 2, I'm going to try to draw those again. I've got some E pointing out. I've got some N points in the same direction. E is parallel with N. So we'll have some flux flowing through there. But on all the other surfaces, let's call maybe this guy here surface 3, this side of the rectangle or rectangular prism over here. E is pointing like this. On the other half, it's over here. E points this way, this way. My normal vector points perpendicular to the surface. E is parallel to the surface. Perpendicular to N. That means their dot product is 0. That means no flux. That's for 3 and 4. There's no flux flowing through these 2 surfaces here. Same with the top and bottom. So maybe we'll call the top side 5 and the bottom down here side 6. Normal vector is pointing up. E is running parallel to the surface. E is perpendicular to N, no flux. So same reason, no flux. So the flux equals 0, flux equals 0. Okay, so the only surfaces we got to worry about are 1 and 2, the front here and the back. Okay, then just for 1 and 2, like let's just look at 1. The double integral of ds, the flux. I already said E is constant on there. I already said that these two are perpendicular, so I can pull that constant E out, ds. So I just want the surface area of that rectangle right there, that rectangle, this guy in front. So he's L by W. H plays no role there. And same with 2, the back. So this is, let me write these, front, back. So the flux, for exactly the same reason, would be ELW. For the rest of them, it's all 0. All the other fluxes are 0. We already said that. Okay, what about charge enclosed? Charge enclosed is always some density times some kind of version of volume enclosed. And what do I mean by volume enclosed? That depends on the units of density. Density here was coulombs per square meter. So to make that coulombs, I got to multiply by square meters. That yellow section right there, that's the intersection of my pillbox and my sheet. So I just want the area of that rectangle times my density. So this will be sigma, my charge density, times area enclosed. That's LW. He's L high and W long. Okay, so we can put all this together. We had 2 different non-zero fluxes. So the total flux total is those 2 added together to, that's where mistakes happen. People forget that too. LW equals sigma LW, and don't forget your epsilon naught here. Hey, the L and the W cancel out. They have to. We get magnitude of E is sigma over 2 epsilon naught. So what that means is, for a sheet of charge, the electric field is constant. There are no variables in there and points away. E is constant in magnitude everywhere. For a sheet of charge, you get a constant electric field in the entire universe. And it has that strength. And then I think I did this one in the other video. But if not, what if I have 2 sheets of charge? What if I put a plus sigma here and a minus sigma here? So I have 2 infinite sheets of charge. What will my electric field look like? Well, from this guy, from positive, we get E's that point away and are constant. All these errors are meant to be the same length. From this other guy, let's choose red. So if this guy here, he's a negative, electric field points toward negative charges. So this guy is going to have an electric field that points toward him everywhere in space, and they're all going to be equal in magnitude. Look what happens over in this region. We get electric field equals 0. All those cancel out. Same over here. Over here in the middle, we get those added together. Here, E is twice the value we got above. Let me not make that one red. In this region, E equals twice from 1 sheet of charge. So we get sigma over epsilon naught in this region. This is what's called a parallel plate capacitor, and that's the electric field from a parallel plate capacitor. Okay, I've already gone an hour. I do want to at least mention the cylinder of charge. I also said I was going to do the sheet 2 different ways. I only did it using the pillbox. We could have just as easily, in fact, easier. We could have done it much easier using a cylinder for my Gaussian surface. And then you only have 3 surfaces instead of 6. But I do want to mention this guy, the cylinder of charge with density, some charge density, rho in coulombs per cubic meter. So I've got an infinite cylinder of charge of radius r. Let me even write here, infinite. So this goes on forever. So I don't want to put any like length or anything on here. I want to find E inside, meaning R less than R, and outside, R greater than. Either one of these can have the equal to. It doesn't matter which one you put the equal to on. Okay, so the first thing I'm going to do is draw a Gaussian surface. I'm just going to kind of set these up to help you on them. So I've got my charge distribution here, capital R. This goes on forever, so I'm not going to put any kind of length on it. But my Gaussian surface does need to be finite. So let's make that cut blue. Little radius, little r here, and length L. That's my Gaussian surface. It exploits the symmetry. It has the same symmetry as my charge distribution. Okay, then a lot of the stuff we just did with the line is going to apply here. We know the electric field points radially out. We know all the flux is going to be flowing through this surface. No flux will flow through the top or bottom. This is a lot like the line of charge. What's going to cause you trouble here, so I'm going to help with this part, is the Q enclosed. Q enclosed will be your density times your volume enclosed. What's volume of this blue cylinder? That's just volume of a cylinder. That's pi little r squared L. There's Q enclosed. Well, we're inside. Dot, dot, dot. And then I'm going to help you on the outside portion. You need to go through all the steps, by the way. I want to see all the stuff I've done on all these other problems. Like write this stuff out. Where is E point? Where is E constant? Where do the normal vectors point? Find the flux through every single side. So you should say here, like, let's label these: the top, the bottom, and the side. I already told you the answer, that flux up here is 0. You're going to motivate Y. You're going to write that up. That's part of writing up a complete solution. Same thing down here. All the flux is going to flow through this third side here. When I say, I'm pointing to these sides. The blue. Okay, then outside. So I've got my cylinder of radius R, capital R. It's infinite. My Gaussian surface now is going to live outside of my charge distribution. So I'm going to have a brand new picture here, little r bigger than big R. I want to draw it in here. Little r bigger than big R. And I have to put a length on here. So now we have this. Okay, now all the other stuff's going to still apply. We're going to find the flux to each side, all that stuff. It's all going to be exactly the same as when we did the line. Everything here is going to be the same for the line for this part of Gauss's law. What about the charge enclosed? My charge doesn't come all the way out to the surface. My charge only comes out to here. The charge lives right here. So the charge is the red cylinder. So that's going to be the density times that volume enclosed, the red volume, not the blue volume. And we can see that that's a cylinder, still has height L, but the radius of that cylinder only comes out to here. So that'll be pi capital R squared L. Okay, hopefully that's enough hints. I can do more with this one next time if I need to. I've gone way over. Let's stop recording.